Today we're going to look at normal distributions. So yesterday we talked about distributions of data, and we specifically looked at dot plots and also box and whisker plots, trying to organize data and decide how they would be distributed based off of how the information is organized. So we're going to see if we can create a dot plot again and just kind of review that distribution. The information that I have listed here is information from an Algebra 2 class. There are 21 students here, which there were 21 students in our class. So I tried to kind of get a range of the heights of the students in the class that would exist for a class of Algebra 2 students. What I'd like you to do is pause the video and below make a dot plot. You can use X's, you can use literally little dots. But see if you can get a graph of this data. And then after you're done graphing it, I'd like you to list the type of distribution that you think it looks like. So thinking about it being skewed left, skewed right, it being a mound or uniform group of data. So after you're done graphing yours, this is what mine looks like. So I didn't make any extra tick marks in between 60 and 65, but I graphed where it approximately would be. And this is the information that I have plotted from the data given of the height in inches of the students in the Algebra 2 class. And if you're looking at this data and you kind of make a curve going over it, you can see that in our class, it looks like most of the people are in the lower height group. And kind of like 70 above is definitely only a few students. I would say that this data for our class would be skewed right. And remember, skewed right means you have the least amount of data on the right side, you have the most amount of data on the left, and that's pretty much what's happening with us. So it looks like the majority of our students are in between that like 64 and 66 inches range. So today we're going to look at a specific type of distribution, and it's called a normal distribution. And this is how a lot of tests are designed, standardized tests. So thinking of the SATs, the ACTs, the AP classes. So a normal distribution has the shape of a bell curve. We'll kind of talk about what that means. So a bell curve is a symmetric curve. Remember, symmetrical. You have half the data on each side of the middle of the graph. And it can be thought of as that mound shape. So a bell curve is a symmetric curve that has the mound shape. So it has symmetry, and the mean and the median are equal to each other when this occurs. So if I think of a normal distribution, I'm going to draw a curve. Try again. There we go. That looks like a mound. And again, in the middle of that mound is our median. And we said the median is that X with a little bar on the top of it, but also the mean. They represent the same value. So this is a bell curve. And again, most tests, standardized tests, we try and get the average to be in the middle. The most amount of students should have about the average. And then you're going to have that smaller handful of students have perfects and a small handful of students that might not perform so well. But we want to try and get the most amount of students to be in the middle of the curve. So we're going to look at some situations today that fit this normal distribution, statistically what's going on with the data. And when we look at the first example, we're looking at the lifetime of 20 100-watt light bulbs. So remember, the wattage is the brightness of the bulb. So we have 20 of these 100-watt light bulbs. And if we kind of look at the data here, we're going to try and make another dot plot and see if this creates a normal distribution. And looking at the numbers here, they're pretty spread apart. So the smallest one, kind of finding the lower extreme, is 970. And the largest one is 1044. So that's a fair range. So maybe we want to kind of count by tens to represent this situation. And I'm actually going to kind of group this together, kind of just thinking about it a little differently so that we can kind of get more of the points, the data values, to align together. So I'm going to make my first tick mark represent the group of data starting at 970, since that was the first value. I'm going to go up to 979. So I am counting by 10, so my next tick mark, I'm counting by 10, should be 980. And then that little tick mark is going to represent all of the values from 980 to 989. I'm just going to continue this method, still counting by tens, but instead of plotting them in between, we're just going to plot them in one group or one bar. So you can be labeling your axes the same way. So again, I'm still counting by tens, but instead we're going to organize the data a little more together. So grouping it together as a group of values. So we're going to make a dot plot, and you can kind of work through this on your own if you want to pause the video and do it yourself and then kind of check your work. But I'm going to go, the first one is 1013. I'm just going to go in order. I'm going to put a little circle where that number, the interval, we can call that an interval of number, a range of numbers. I'm going to place it within that interval. So again, pause the video, see if you can create your dot plot. If you'd rather use X's, use X's. Okay, so this is what my graph looks like. Again, hopefully you have a graph that looks very similar. And the first question that we want to think about is, does the data create a normal distribution? So a normal distribution, we should have the highest point in the center of the graph. And then we should have the data kind of spread apart on the left and the right. And I know that that group at the 990 to 999, I know that group has 5 data values in it, but if I kind of make a curve, this looks very close to a normal distribution. And when you think about products and creating products that you want to last for a certain amount of time, we do want the average product to last for that middle value. So most of the products we want to kind of be in the average. And then you're going to have a few of them that end up lasting longer than others would. So there's a couple other questions that are down below. And the first question underneath it says, what is the standard deviation for the light bulb in this data set? So again, pause the video. Do this on your own. Pause it and plug these numbers into your calculator. We want to find the standard deviation and we want to find the mean of the data set. And we talked about these two numbers before. Remember, the standard deviation we want to pull is the SX. That's the sample, because this is a sample. It's not all of them. So there aren't only 20 100-watt light bulbs. There are millions of 100-watt light bulbs. So that's why we want to use the SX, the sample. It's a group of it, but it doesn't represent all of them. And then the mean is that X with the little bar on the top. So pause it. See if you can figure out the standard deviation and the mean. So after you do that, the next question underneath is a little more involved. It says, what percent of the data points fall within 2 standard deviations of the mean? So the mean, remember, is in the middle. And if we are within 2 standard deviations of the mean, that means we could go above the mean, above the middle, or we could go below the middle. And we're going to see if we can figure out what 2 standard deviations of the mean would be. And in order to do that, if you take the mean that you just calculated, which we have as a 104.17, and we're going 2 standard deviations of the mean. So I'm going to take the standard deviation and multiply it by 2. Makes sense. And then if we add them together, we get 138.65. So when we were doing outliers, kind of a similar process, but now instead of doing an outlier, we're finding out that like the kind of end point of where 2 standard deviations would be within our data. So that's like the highest point of the 2 standard deviations. We're going to do the same thing, but we're going to find the lowest point, because if you have the mean, you're in the middle of the graph. Well, the middle has a left and a right, so we're trying to find that borderline or the boundary of the left and the right values. So a standard deviation could also be lower than the mean as well, 2 standard deviations. And that lower number, if I calculate this, multiplying and then subtracting, we get 969.65. So those are kind of our 2 boundary numbers. Look in your data, see if you can count the number of values that would be between or within these 2 standard deviations. So what percent of the data points lie within 2 standard deviations of the mean? So I know I have 20 data points that are listed up there. How many of them? Just count. So literally go to the list and count how many numbers are within 1038.65 and 969.65. Or you could say which one is beyond those, or which 2 are beyond them, whichever way you want to think about it. And if I count through all of them and look at them, 1044 is not within those 2 numbers, but that is the only one. All of the other ones are between the values. So it says, what percent of data points lie within 2 standard deviations? Well, 19 out of the 20 of them lie within 2 standard deviations. 19 out of 20 is 95%. So 95% of the data would be within 2 standard deviations of the mean, 2 standard deviations from the middle. So we're going to kind of talk about that information a little more. And there's something called the empirical rule. The empirical rule is generally how statistical sets of data tries to conform to. So tests, standardized tests, products like a washing machine or a refrigerator, when they're created, they generally apply to the empirical rule. And the empirical rule talks about the number of standard deviations that data is from the middle of the graph. So there are 2 graphs that are drawn below that represent the empirical rule. And the first part underneath says the mean is the X with the little bar on top. And then the standard deviation in this case is actually the little theta symbol. And we're using that theta symbol because this represents all of the data, whatever is existing in the whole entire group. So the total area under our curve. And if I have a curve and I want the entire amount of the area underneath the curve, we're thinking about percentages here, and the entire area under a curve that's shaded is 100%. Pretty much we're saying every piece of statistical data has to lie underneath this curve. So then there are 3 little bullets, and those 3 bullets represent the amount that's supposed to be within the mean or the middle of the graph. And the first bullet says about blank percent of the area under the curve lies within 1 standard deviation of the mean. And if I look underneath, this notation is a little weird, but 1 standard deviation means we're moving to the left or to the right of the middle. And you have that little x minus theta, so you're moving left 1 standard deviation, and x plus theta, you're moving right 1 standard deviation. And that is 68% of the data, and you can see that it's labeled there as well for you. So 68% of our data is supposed to be within 1 standard deviation of the mean. So the majority of it should be pretty much around the middle of the graph. The graph on the right side shows you splitting it left to right. So 34% on the left, 34% on the right. But together, 1 entire standard deviation from the mean, left or right, is 68%. But again, moving left half of it, moving right the other half. The second one, 2 standard deviations of the mean, is the number we calculated above. We found that 95% of the data from the example with the light bulbs was 2 standard deviations from the mean. And if I look at that graph, 2 standard deviations is 95%. So most of the data values, when you have a statistical survey of information, should be within 95% of the middle. What that really means, if I look on the other side, I already have the 64%, which is the 34 on the left, 34 on the right. So then I'm adding another 13.5% of information and 13.5% again on the left and the right. So really, this 2 standard deviations that still represents 95%, but we're just splitting it apart, thinking about a left side and a right side. The last part, it says, is 3 standard deviations, and that's 99.7. So essentially, almost 100%, but not quite there. And that 99.7% of the data should be within 3 standard deviations of the mean. And that means that you're going to have that little percentage, teeny tiny, the 0.03% being left or to the right beyond those 3 standard deviations. But the empirical rule uses the 3 standard deviations. So again, looking at that percentage, if we split it up thinking about left and right, we already had the 95%, but now we're going an extra 4.7%. So if I divide that by 2, I get that little 2.35, which is this little teeny space under the curve on the left and the right, but that really is the 99.7%. So that means then that leaves us an extra 0.15% on each side of the graph to get us the 100% of the curve. So this is called the empirical rule. It does not change. So any type of statistical data, if it's 1 standard deviation within the mean, it's 68%. And again, that 1 standard deviation consists of moving left and right of the mean. 2 standard deviations is always 95%. So if I have data that fits to the normal distribution or the empirical rule, then that information should be 2 standard deviations away from the mean would be 95% of the data. And then again, the last one, about 99.7% of the data would be 3 standard deviations from the mean. A standard deviation is the spread of the data from the mean. So the further you're spread apart from the data, from the mean, means the less that it is associated with the middle of the graph. So we're going to look at an example on the next page. See if we can try and apply these standard deviations. And we have a lieutenant governor's salaries. So this is not our governor's salaries, but instead lieutenant governors. And these are the salaries from 2016 to 2017, their annual salary. And it's of the 43 state lieutenant governors. Not every state has a lieutenant governor, so 43 state lieutenant governors. It says they have a normal distribution. So that means if we plotted all of their salaries, it would be that shape of a normal graph, a mound curve. It has a mean of $87,000. So of the 43 state lieutenant governors, the average salary is $87,000, the mean, the middle salary. And then their standard deviation is $22,000. That would be the spread of the data, how far above and below the mean it would go. So part A, within what range do about 95% of the lieutenant governor's salaries fall? So 95%. Within what range meaning what's my lowest and smallest value, what would those boundaries be, where you'd have 95% of the lieutenant governors. If I go back to the previous page and look at my empirical rule, 95% is supposed to be 2 standard deviations from the mean. So I want to decide or figure out what would those numbers be that represent the boundaries of 2 standard deviations. And I can do that pretty easily by taking the mean that was given, which is the 87,000, and adding 2 standard deviations, or taking the standard deviation and doubling it. So that gives me that number on the right, the number that's above the middle of the graph. And putting that in your calculator, remember these are dollar values. So 2 times 22 is 44. 44 and, we're looking at 44 and 87. So add 44 and 87 together. And we get 128,000. So that would be the highest value. And then if I do the same thing, take the 87 minus 2 standard deviations. Again, we're looking at 87 minus 44, or 87,000 minus 44,000. And that gives us a lower end of $43,000. So within what range do about 95% of the lieutenant governors fall? Well, their salaries fall in the range from $43,000 to $128,000. That would be within the range of my data. So 95% of the salaries of those 43 states are between $43,000 and $128,000. The second question says about what percent of the lieutenant governors have an annual salary between $65,000 and $109,000. Well, I can do this problem pretty much like we did above, or I can do this problem with a little picture as well. And I'm going to draw the picture to kind of show how the above information supports it, and to show you that really you can do this problem or approach it 2 different ways. And this is how your homework is going to look. So just so you can kind of see how we're going to graph or think about the homework. So we're going to place the mean in the middle. So this is another way to think about the spread of the data. I'm making myself a normal curve to represent the spread of this data. And the mean is the 87,000. So now if I go above the mean 1 standard deviation above the mean, meaning I'm taking the 87,000 and adding 22 to it. So that gives me 109,000. That's 1 standard deviation above, which represents 34%. If I do that same thing below and I subtract 22,000, so 87 minus 22 is 65,000, I get, again, 34%. That's based off of the empirical rule. So the empirical rule says 1 standard deviation from the mean should be 34% above and 34% below. Well, if I total that together, that gives me that 68%. 1 standard deviation is 68%. I'm going to continue this just to kind of show you how to work through this problem. If I go 2 standard deviations from the mean, that's how I get the numbers that we have calculated above. If I continue to add 22,000 to 109, we get 131. I have a mistake up here. I added wrong. Let's fix this. So now I have 131. And if I subtract 65, or 22 from 65, we end up with 43,000, which is what we have above. So looking at the next 2 values, we said it was 95%, the total amount. Well, that means I have to add an extra 13.5% to either side. So that's how I would get then 2 standard deviations of 95% or 1 standard deviation of 68%. I'm going to finish this just one more time just to show you again how a normal graph would be distributed. So the empirical rule is 3 standard deviations. If I continue to add, I would add another 22 to 131. That gives me 153. Or I would subtract 22 from 43, and that gets me 21,000. And that should be 2.35 on either side, because 3 standard deviations is supposed to be 99.7%. And that little leftover one is the 0.15% on either side. So this would be how the empirical rule looks when you're applying it to information. So if I finally want to answer the question after all of that, I can see that it matches with the information that I got from A. 2 standard deviations moving left and right makes 2 standard deviations. 95% of the data lies between 43,000 and 131,000. My next question says about what percent of lieutenant governors have an annual salary between 65 and 109. Well, if I look at my numbers of 65 and 109 and add those two percentages together, I get the 68%. So 68% of the data lies within those two values. So I'm going to stop there because I want to kind of explain the homework. We'll look at example 2 tomorrow, but I'm going to go to your homework worksheet just to explain what you're going to do, because part B is really how we're going to think about the homework worksheet. And it's set up a little differently because it's kind of using the formula and the general information from the formula. So here we're really not using a word problem. So when you're using a word problem, you actually have data that you're using and applying. However, here it's just the formula. So we're just going to apply it to the formula. We don't have a real life situation like kind of to think about, but this is just, can you understand what the notation is representing? So the first problem here looks a little weird. We want to find the probability or find the indicated probability for a randomly selected x value from our distribution. And it says it's a normal distribution. So a normal distribution uses the normal curve and the empirical rule. So I'm going to just draw that above here, just like we had. This is in the notes. It was on the page of notes that we were just working on. So there's our mean, the middle of the graph. All right, and then we're going to go 1 standard deviation above and below, and I would write that as x bar this doesn't want to work for me, Addie. My picture just isn't cooperating with me right now. So x bar minus the mean, or minus the standard deviation, and then the x bar plus the standard deviation. And this, of course, is not cooperating with me. I'm going to see if I can go above my picture and draw you an empirical rule here. All right, so I just want to show you the empirical rule drawn out. So there's my mean, 1 standard deviation from the mean. So that means I would have the x plus the standard deviation and the x minus the standard deviation. And that would be 34% on each side. Okay, So now, two standard deviations would say x, the mean, minus the standard deviation, or the mean plus the standard deviation. That's 13.5%. And then if I go a third standard deviation, so my mean minus 3 standard deviations, or my mean plus 3 standard deviations. That is 2.35%. And then the last little percentage left is the 0.15. So that's the empirical rule. We're going to see if we can apply the empirical rule to what the first question is asking. So it says find the probability that a number is greater than or equal to the mean. Well, if I look at my little chart, the mean is in the middle. Probability can be a percentage or it can be a decimal, but it's always less than 100 or up to 100. So this question is saying what's the probability that a number would lie above the mean, greater than or equal to the mean? Well, greater than or equal to the mean would be everything to the right of the middle value. And if I add those percentages together, you are in the middle if you're at the mean, so half of it should be on the left and half of it should be on the right. So that should be 50%. So number 1 should be 50%. And then if I go to do the second problem, the second one says we want a number that is 2 standard deviations below the mean. So if I go to 2 standard deviations, in my graph above here, and I find out where that 2 standard deviations would be, here's my location of 2 standard deviations. That's this line right here. That's 2 standard deviations. Well, I want the value to be below it. So if I'm going below 2 standard deviations, I'm adding 0.15 and 2.35 together. That would be if my x value lied within 2 standard deviations of the mean. So we would add those two together and get 2.5%. So that's what you're doing for the first 3 questions there. You're going to use the normal distribution, the empirical rule, and you're finding out the percentage that the value applies to. You're going to do that again in part B. So those first 3 questions in part B are the same type of questions. So you're using this chart, the empirical rule, and then you're applying that chart to the question. The other part of it, 4 and 5, say what percent of the data is in the shaded area. So again, you're going to look at your little chart here, the empirical rule with the percentages, and look at the shaded area and add up the percentages together. So that will represent the percent under the curve. The other type of problem we're going to do would be 6 through 11. And I'm going to show 6 through 11 down below here. Give myself an extra piece of paper. So numbers 6 through 11, you are going to draw your own curve. One curve answers all of the questions. So this is in 11.3 part B. You are going to create your own curve with the information that's given. A normal distribution has a mean of 27. So 27 is the mean, that's in the middle. And then continuing, it says a standard deviation of 5. Find the probability that a randomly selected x value from the distribution is in the given interval. So I am going to make a chart that represents a normal distribution with the empirical rule. And if I have 1 standard deviation from the mean above or below, I would add the standard deviation of 5 and I would get 32, which would be the marker above. And if I go below and subtract 5, I get 22. So I can see for question A, what's the percentage or the probability that a number is between 22 and 32? Well, here's 22, here's 32. Add those percentages, that should be 68%. You're going to continue the graph. So you're going to continue adding the standard deviation. So you're adding 5 to 32, and that gives us 37. That percentage is 13.5%. And then you're going to subtract 5, and that makes 17. That percentage is 13.5%. You're going to continue on because we have 3 standard deviations for the mean. So 2.35, and then the last is 0.15. So finish the chart. Once the chart's finished, you should be able to then answer questions 6 through 11 based off of the one diagram. You're going to do that same thing for that third part in 11.3 practice A. So you're going to make your own curve for 6 through 9. One curve answers those 6 questions. If you have any other questions, feel free to email me. Hope you have a great day.